Cool. So moving on, I hope you guys are back now. So we'll just do a quick recap of what all we have learned up till now. So let's start then. So basically, this is going to be the most important session of most important part of this today's session, because we are going to know how basically neural networks works. Okay, and yeah, it's not magic. So if that's the answer popping in your head, then you're wrong. Okay, so let's move ahead then. Let's do a quick recap. So what all we have seen up till now. So first we saw what weights are. So now here in the GIF, please just ignore 7, 84 and 16, all those numbers, just ignore them. All you have to see is that there's all the strings, and this is basically a neural network, okay? And that's all you have to see right now. For now, don't go into the details of what those numbers are saying. So yeah, so what are weights? So first we saw what weights are, and as the name suggests, weights. Okay, what does weights mean? So basically weights are nothing but they signify a weightage of a particular input to our final output. Yeah, so like the name weight is basically taken, it just signifies the weightage of our input to the output. So those are weights. So we first saw what weights are, and weights are represented and will be represented everywhere with the word W. Then we saw what biases are, and yeah, now we'll see what is the significance of a bias, because I saw a lot of questions there were popped in. So yeah, so basically we saw that the equation that we were seeing in the earlier examples were basically of type something like this: y equal to mx plus c, where m was basically w, which was our weight, times the input x plus some c, and c was nothing but our biases. So look at this example here. So suppose for this example, y equal to mx plus c, basically this is a line equation having some intercept c, and if we remove that c from that line equation, what do we get here? We get a line passing through the origin, right? So think of it as like this. Suppose we remove the bias from our examples, then what will our neural network do? Neural network will predict y's, which are basically all those outputs will be basically some linear outputs, which on computing will pass through the origin. And yeah, our real data wouldn't be like this, right? What if our points lie here? So suppose we have some data which we are going to be represented by some x and y in here, and suppose our point is somewhere here, and that's what we are expecting. And suppose we remove the bias from here, then yeah, this is the line. This will be the prediction that our neural network will do, right? And here we are going to have a point. So basically what our neural network is doing is it's just predicting the wrong output, right? So yeah, so that is basically the significance of biases. So moving on, what did we see? We also saw that how we compute the weighted sum of the weighted sum plus a bias we add to that, and this whole equation, let us call z as the whole equation, which is basically wx plus b. And then what we do is that we pass this z to some function. Yeah, so what was that function? Yeah, it was activation function. I know you must be thinking what activation function is, but don't worry guys, all those things will be cleared right now. So for now, all we have to remember is that we had some function, and it was taking z as an input, and whatever the output it was giving was basically the output of a neuron. So this is all that we have learned up till now. So that was a quick recap of everything. Now moving on. So have you got, like, just a question, have you ever guys, just think upon just random anything, just whatever you think, just tell me what do you think, how do you think a neural network works? Like, how does it predict? Just tell your answers in the chat box. The question is, what do you think, how does a neural network predicts the output? How does everything happens? Come on, just, yeah, and dare you say magic, because magic is certainly not the answer. Yeah, hit and trial, yeah, kind of, you're going to them based on bunch of method. Yeah, cool. So basically it is nothing but calculus, okay, and obviously not magic. Again, I know some of you may be thinking magic. Oh yeah, you got it there. So yeah, it's not basically magic, it is just calculus. Okay, so we'll see what this calculus part is and how these things go. Okay, cool. So let's move on. So a quick recap we have done. We saw what weights are, what biases are. We then saw what Z is. We also saw what a perceptron is, how a perceptron performs or how does it does things. So basically this was the perceptron we saw. We gave some inputs, it has some weights and biases, and basically some there happened some solving of equations. That was here, that's the Z part, and then that was giving us the output. So moving on, as you so basically forward propagation is how our neural networks predicts. Okay, so this is the process how this is the process basically through which a neural network predicts an output. Okay, we are not going to see if the output is right, wrong, or right, but just the way it predicts output. This whole process, right from putting inputs, giving inputs to our neural network to the end where we get an output. This whole thing is basically forward propagation. So yeah, what is forward propagation? So for our example, just consider this as a neural network that's on the top right corner. So we have some inputs here, that's our input layer. Then we have some hidden layer here, and the output layer or is the basically which spits out our output or our prediction. So yeah, you as you guessed it, it's basically solving it's basically solving of some mathematical equations to get a particular output, and that is what forward propagation is. You might see somewhere it is written as feed forward, and that's also correct. So that is that's also a correct way to say forward propagation. So input data is forward propagated through the network layer by layer to the final layer, which outputs a prediction. And this thing is called this whole thing is basically called as forward propagation. In mathematical terms, you can say that it is basically solving equations to find out an output. So that we can say that it's basically solving equations to get a output. So that is also for propagation. So just for example, if let us consider this example. It's a single perceptron. We have some inputs x1, x2, x3. Then we have some weights associated to it, w1, w2, w3. And then we do some weighted. And then what we do is we do the weighted sum. Sorry. Then we do the weighted sum, and then we add a bias to it. And basically, whatever that weighted sum and bias is, like now we are going to say this whole thing, weighted sum plus bias, as Z, and then we pass on this Z to a function that is our activation function, and then this activation function gives out the output, and that is our prediction. So okay, what activation function is? So I know a lot of people may think what is activation function, guys?
Okay, guys. I hope.
Yeah, I'm back.
Yeah.
Cool. Am I audible and visible?
Yeah, both.
Yeah, as you guessed it. Yeah, some of we were here. Yeah, we were thinking about what activation functions are. So what activation function is, you're gonna see it forward. And yeah, as the great Andrew Ng quoted it, that don't worry about it if you don't understand it. Okay? Yeah, I said it. Don't worry about it if you don't understand it. So yeah, we are going to see what activation functions are in the upcoming slides. So moving on to the next slide. activation functions. So basically here we are going to see some of these functions. Basically activation functions, mostly what we are going to see is graphs and why do we need activation functions. So we're going to see each and every part of it. So let's move on. What activation function is? It's just a function that you use to get the output of a node. And here node, by node we mean the neuron that you saw earlier in the earlier images, right? So activation function, it is also called as a transfer function, and there are a lot of types of activation functions. Like earlier in the first session you saw that there was a sigmoid function which was basically 1 upon 1 plus e to the power minus of x. So there are a lot of functions we are going to see, activation functions that we are going to see. So moving on, why do we even need an activation function? Why can we not just do y is equal to weights times the input plus a bias? Why do we even need an activation function? So the significance of an activation function, this is the important part and you have to listen, and don't worry, you're going to know all of it. Okay, so activation function, basically what activation function is, it decides whether a neuron should be activated or it shouldn't be. So the purpose of activation function is basically to introduce non-linearity into the output of a neuron. Now there are these big words, non-linearity and whatnot. Okay, even I don't know it right now, but yeah, you're gonna know it in the future slides, so just hold on there. Non-linearity, we're going to see what non-linearity means here. So basically what activation function does is, there are a lot of times we have networks. Suppose there's a classification network which predicts in basically two ways, if it's a yes and if it's a no. So we obviously can get an output saying that yes, whatever you input you give is a yes or no. So we basically assign two values, yes is equal to 1 and no is equal to 0. And so sometimes what we need is that we need our output to be in a certain range, that it should be between 0 to 1. And that's why sometimes that is also another reason why we need activation functions. So let's move on. So there are basically two types of activation function. First is a linear activation function, and then we have non-linear activation functions. Earlier you saw sigmoid function, which is basically an S which ranges between 0 to 1. Then we have leaky ReLU, we have hyperbolic tan H, we have ReLU, and there are so many functions. But here's an important question. Why are there linear and non-linear things? Like, why is there a linear activation function and a non-linear activation function? And how would we know like where to use which function? It's like, because there are so many functions, right? There's linear, there's non-linear, like which and where should we use one? So random guesses, like, what do you think? Like, why do we even need some of these? Why do we need linear or non-linear functions? Anyone? Okay, we'll just move on then. So, okay, let us see why do we need non-linear or linear functions. So let's move on to our Jamboard. Okay, cool. So is it visible, Mir?
Visible. Sankit, can you first give them examples what are actually linear and non-linear activations?
Yeah, first we'll just get into what examples. Yeah, so linear, okay, we'll just see with an example over here only what linear functions are. A linear activation function is, as the name suggests, linear activation function is a function. Let us consider g of z as a function, and it gives an output y, right? So what linear functions are, basically it takes an output z and it will give some linear combination which will be like y mx something, right? Those are basically linear functions. To know more about linear functions, we'll just take an example of this slide. We saw a lot of functions here. So basically yeah, we'll consider an example of tan h. So this is a non-linear function, right? You can see how it gets bent over this value of x equal to 0, and then the output changes from -1 to 1. So that's a non-linear function. And yeah, I guess there's the same tan h here. And then we have a lot of functions. We also saw sigmoid function, right? Yeah, sigmoid function. This is basically a non-linear function, that is it's the graph of which would be non-linear, so that you can understand as a what linear and non-linear function would be. So we'll just go on to why do we need non-linear functions, activation functions. So consider this example. So we have a simple, or the simplest neural network here. So we have inputs x1. So we have inputs x1, x2, and then we have some inputs x1, x2. Then we have some weights w1, w2, w3, w2 here in the second layer. So basically this is our input layer. In the second layer we have two neurons, a1 and a2. And then in the final output layer we have a3, which is basically our output. And here we have weights w5 and w6. So let us compute the equations and let us see what each of these neurons output will be. So on solving equations, for the first just a second. Yeah, so upon solving equations, what we get for the first neuron is that its output is basically w1 times x1 plus w2 times x2, w3 times x2, the weighted sum. Basically its weight, and it's this weight and the input, this weight and the input. Similarly we calculate for this neuron, its its output would be z2, and similarly for this the output neuron, its the weight is the output will be this. Now just a recap what our equations were. So basically what our equations were, z, we saw that z was something w times x plus some b, and then what we did was we gave this whole z to some function which was g of z, suppose we consider, and this whatever the output of this function was basically the output of our neuron, and this was our final predicted output. So now we'll consider a case where we don't have this, where we are not including any, where we are including a non-linear function. So okay, so now we calculated z1, which is basically the output of this a1. Then we calculated z2, that is the output of a2, and a3's output, which is z3. Now let us substitute. Yeah, and for a3 its input will be a1, its input will be a1 and a2. So now let us substitute the values of a1 which we calculated here. So let us substitute these values in a1 and a2. So upon solving this equation, what we are getting here is that we'll just solve the equations, and upon rearranging these equations, what do we have here? We see that Z3 becomes some weights, addition of weights times input x1, again some weight, and then x2. So is it okay if we consider this as some weight w8 and this as some weight w9? Yeah, so obviously this is some, it can be considered as another weight, right? Because it's just addition of weights. So finally what we are getting here is the equation is nothing but some weight times input x1 and some another weight times input x2. So basically what is happening here is that our weight, our inputs x1 are basically going directly to the neuron through some weight w8 and through some weight, suppose w9, and and some weight 9, and so there's no use of these layers, right? If we are there's just no use of this these neurons, right? And all we are seeing is that it is just some linear combination of weight times x1, some weight times x1 and weight times x2. So what do we infer from here? we infer from here is that our whole neural network, which had one layer, is basically performing like a perceptron, which we saw in the earlier example. Because it was, what is a perceptron, right? We saw perceptron was some weight x plus b. That's what our our perceptron was giving. And so basically this whole neural network without any activation function behaves like a perceptron. So that is why we need nonlinear activations. Suppose we had some activations here, then that wouldn't be the case, right? Suppose this Z1, our first neuron, had an activation function G. So the output of this would be some G times Z, and if this A2 had some function, then it would be G times Z2. So if we had a non-linear activation functions, then maybe this wouldn't be happening, that our first input is getting directly to the output layer, and it wouldn't have been behaving like an perceptron. So this is so basically that is why we need a non-linear activation function. So now let us move on to the slide. Okay, so we saw why do we need non-linear